Testing on YouTube. Testing on YouTube.
Welcome to Rover. As pet parents and pet lovers.
Jesus Christ. Testing on YouTube. All right, it works nice. How's it going? Jan Renner and Sam. Jan Renner asking, we want R1, please. You can still ask questions about the R1 paper. I'll totally answer it. How's it going, Sarah? All right, now let's make sure that X is live, and then we can go ahead and get started. X is not live. What's going on with X? Let's see, let's try again. Okay, X is live, perfect. All right, everybody. How's it going, Mark B? All right. So let me start the stream. How's it going, NLP prompter and Ed? All right, everybody, welcome to another Who Posts stream. Today we're going to be talking, we're going to go deep into the math world. We're going to be talking about relative entropy. But before I do that, I have something to address, and that's this new weird haircut that I have. So I figured what better way to see which model is better than by getting them all to roast my haircut and see what they think. So Grok 2 should apparently be the funniest AI, but I thought this haiku wasn't as good. Bald head gleaming bright, eyebrows lost in the vast sea. Where did hair go, friend? It's about a 5 out of 10. How about Gemini Advanced 2.0 Experimental Advanced, right? The most advanced Gemini model. A shiny new head reflects light in all ways like a cue ball gleams. I would almost say the Grok one might even be better. And then this one here, right? ChatGPT O1 Pro, it had thought for about 2 minutes and 8 seconds. Really the most extreme amount of intelligence that humanity has to offer right now. And here's the haiku. Bare scalp shining bright like a peeled egg in the sun. Hair fled in sheer fright. And I think this one wins. To me, this one is by far the best. I'm a little bit surprised that none of them had anything to say about this goatee, because to me, that's kind of the most heinous part of this entire haircut. But I guess they all just kind of focused on the fact that I don't have any hair. But, all right. Let's get into the actual work of it. All right, so relative entropy. Relative entropy is another term for KL divergence. And KL divergence is something that you see pop up time and time again in pretty much every single machine learning paper. Maybe not every single machine learning paper, but lots of machine learning paper, and especially reinforcement learning papers, right? So here we have the DeepSeek R1 paper, and you can see that this is the actual optimization objective, the new technique that they call GRPO. But you can see here this term right here with a little hyperparameter in front of it, this beta, this DKL, right? This DKL has two little things here. It has this pi theta and then this pi reference. And those are the policy and the reference policy. So you have this KL term here in the DeepSeek paper. Here's Kimi K1.5. This is another Chinese startup that basically did a very similar thing to DeepSeek, right? They used RL to basically iteratively improve a model. And you can see here it is again. They didn't use the DKL, they used KL, but the same thing, right? You're doing this KL divergence, this relative entropy between pi theta and pi theta I. So in this case, it's policy, right? So anytime you see this pi theta, that's a neural net. That's a neural net with theta. Theta are the parameters of that neural net, right? And what you're doing in these is you're putting these inside your loss functions, and because you don't want this thing to drift too far from that, right? Here it is in auto-encoding variational Bayes from Kingma, right? Kind of royalty in the machine learning world. And here it is, DKL, same thing, right? So what the fuck is DKL, right? So if you've been around the machine learning world, this might be kind of what you know about it, right? It's a distance metric between two probability distributions. It's not symmetric. Order matters. It's good as a regularizer to prevent the policy from drifting too far, right? That's kind of the top of the iceberg. And honestly, that's kind of where I was at, you know? But then I realized, you know, if I really want to master something, I got to teach it. And this YouTube channel is kind of a version of that, to be honest. So that's what today is going to be about. It's going to be really diving deep into what exactly is this KL divergence or relative entropy? Where does it come from? And why do we keep using it everywhere? All right. And if you're into that, you can join me on my journey. All right. How's it going, Pratik? Can you explain this again? The relative entropy, or I'm not even sure. Okay, so GPT-O1 Pro and Gemini Advanced. So these are kind of probably the most advanced AIs that we have right now, and I asked them, right? Tell me about KL divergence, right? So pretty much all of them give you the basic formula here, right? KL divergence is between two distributions, distribution Q and distribution P, right? So the way that it's mostly used is that usually P will be the true distribution of the data, while Q will be the actual model, right? The neural net, right? So that's one way to think about it. Generally, in a lot of these, you're more so using it between two neural nets, right? Two policies that are both neural nets. Maybe one of them, for example, in this one, pi theta versus pi theta I might be a neural net that's kind of done a little bit more of this iterative training versus the policy from a couple steps ago. Maybe it's like a expected moving average kind of situation, right? But it's basically a distance metric between two probability distributions. It measures how inefficient it is to assume the distribution Q when the true distribution is P. Here's Gemini. A simple interpretation of the KL divergence of P from Q is the expected excess surprise from using Q as a model instead of P when the actual distribution is P, right? So expected excess surprise, inefficiency, distance metric, right? It seems like they're all coming at it from different angles here. So one thing to realize here is that whenever you see this formula, right, the sum for all x and x, right, this is a discrete version of it, right? If you have a discrete set of samples x from these distributions. But there's also a continuous version of it, right? So here in continuous or more general measure theoretic settings, the sum is replaced by an integral. So here's the more continuous version of it, right? So DKL of P and Q, or P into Q, and then it's not symmetric, right? So if you switch to Q and P here, it wouldn't be the same. But you can see here, this is the continuous run, right? Where you're integrating this from negative infinity to infinity. So you're going from all the way negative infinity, which is all the way over here, to infinity, which is all the way over here, right? And you can see here we have two, in this case, Gaussians, P of X and Q of X. You see they're not quite aligned, right? So they're not quite the same distribution, right? So we can expect the DKL to be some positive number. And this integral is literally just the area under this, right? So if you took the area under that, the integral from negative infinity to infinity of this, with respect to the x-axis there, you would get some number, and that number is the KL divergence, right? So the KL divergence can be a big number, it can be a small number, and it can also be zero, right? If it's the same exact distribution, you're just going to get zero. So here's, for example, let's say you had this distribution PD, right? And you had this distribution PG, right? So in this case, the PG is really only accurately modeling this kind of 1/2 of the distribution of this PD, right? So the KL divergence of PD to PG is very high, right? If you go this way, right? So now this is basically the same as this. You've now swapped it, right? PG to PD, and it's only moderate, right? So which one you're actually using as P and which one you're actually using as Q ends up determining the value. So even though PG and PD here are the same things, you're going to get a different value for the KL divergence depending on which order you do here. Okay. Hence asymmetric. Yeah, Pratik definitely knows his math a little bit. Policy drifting too far means. So what I mean by this prevent the policy from drifting too far is that a lot of times, or at least in the way that I've seen this KL divergence within reinforcement learning, is they'll add it as like an extra term inside their loss, right? So they have the loss that they actually want to use, or the thing that they're trying to increase using reinforcement learning, right? Reinforcement learning, you have this reward function that you're trying to say, we want to maximize this thing, right? So usually the KL will just be like a little extra term that you add at the end here, right? That's why you have this hyperparameter, because this beta is going to be some small number, like 0.001, right? Because you really want most of the stuff, most of the learning, most of the gradients that are going into your neural net to come from this GRPO, but you're adding this little DKL here with a little number in front of it just to make sure that as you're pushing gradients into this policy, it doesn't drift too far away, right? If you push gradients and the new policy, right, this theta I versus the theta I minus 1 versus the theta I minus, if it starts drifting too far away, right, if the distributions start looking too different, you want to penalize that. You don't want to kind of drastically change your policy every time. That's kind of what I meant by the prevent the policy from drifting too far. I missed the new haircut. Yeah, I started off with a little joke here where I kind of got a bunch of different AIs to roast my haircut, but they were all just roasting the fact that I'm bald, not the fact that I have a weird, shitty goatee now. Okay. Let's go back. Where does this actually come from, right? Because we keep using the word KL divergence. Like, why do we call it KL divergence? So the reason we call it KL divergence is because it comes from these two guys, Kullback and Liebler. And this is the original paper. So this is in 1951. Ancient paper at this point, on information and sufficiency. And specifically, this is where they do it. So here you see f1x log f1x over f2x, the integral over e, right? So that's effectively just the continuous version, right? It's basically this. And they call it the information in x for discrimination between h1 and h2. This means information for discrimination between h1 and h2, where h1 and h2 are basically analogous to your p and q right here, right? So that's the original KL divergence definition. So who are these guys? Who are Kullback and Liebler? So this is Kullback and Liebler. Both of these guys are already dead, right? You can tell 1907, died 1994, born 1914, died 2003. So these guys were basically like code breakers. So they worked at the NSA, right, post-World War II. This guy helped crack the Enigma machines in Britain, so he probably knew all the guys, right? He knew von Neumann, he knew Turing, he knew, who else? Shannon. Like, all those guys were basically all in the same places, right? Which is the military intelligence and kind of code cracking groups that kind of morphed into these kind of weird research institutions after World War II. So this guy, Kullback, supervised a team of about 60 people, ended up developing things like memory, such as magnetic tape and drum memory. Here's Richard Liebler, celebrated Venona code-breaking project, worked in the National Security Agency, director of the Communication Research Division and the Institute for Defense Analyses, right? So basically these guys were trying to figure out, we're really there at the beginning of kind of information theory and like how do you use that to crack codes. That was like kind of the original reason that almost this entire field started, right? Okay. Pratik, min negative KL divergence shouldn't overall, we want to minimize the distance, but in the loss form, isn't it overall maximizing KL? Yeah, so minimization, maximization, like, it doesn't matter, right? If this was a loss function, I want to minimize a loss function. If this is some kind of reward, I want to maximize that reward, right? But then I can easily just, maximizing the negative of the thing is the same thing as minimizing the thing, right? So you can always just kind of arbitrarily add a negative or a positive depending on like what you want to do, right? Do you want to bring these two distributions closer or do you want to bring them further apart? Yeah, in RL, a lot of times the way that they write these, it's more like this is the reward function. We want to make this as big as possible. But in machine learning papers, usually the way it's formulated is this is the loss function. We want to make this as small as possible, right? So machine learning people will say we want to minimize the loss. Reinforcement learning people will say we want to maximize the reward. But maximizing the reward is the same thing as minimizing the negative reward, right? It's like any minimize, maximize, you can just add a negative sign and just flip it, and it's the same thing. Okay. All right. So maybe just one meta point on these two guys, right? Because I've gone down this rant before, but this is one of my personal pet peeves, right? So here you have a guy about to click 2 red buttons, and there's 2 decisions here. You can call something, name it something that helps explain or understand the idea, but nobody is going to remember you. Or name it based on your last name and force people to remember you, right? And unfortunately, a lot of math and physics PhDs, they care more about their ego and their career than actually helping people understand the idea, right? So whenever these guys come up with an idea, what they really care about is putting their name on that idea, right? What they want is they want their name on that idea so that people are going to remember them, right? And math and physics is like particularly bad about this, right? So here's a random Wikipedia screenshot, and you can see, look at all this stuff here. Whitehead's theory, Brand's-Dicke theory, Einstein-Cartan theory, which is also called Einstein-Cartan-Siama-Kibble theory, right? It's like these names don't help you understand what the actual idea is. They're really just vanity names that force you to remember the people who came up with that original concept, right? So KL divergence is one of those vanity names, right? Where you're kind of like using up your limited brain compute to store this guy's name, this guy who's long dead and doesn't matter anymore, rather than calling it what we should call it, which is what I call this stream, which is relative entropy. So this is really what we should be calling KL divergence, is relative entropy, because this name helps you understand where this comes from, right? It comes from these ideas of information theory and entropy, and that helps you understand the concept, which is why I'm going to call it that. Okay. So as we said, KL divergence comes from, or relative entropy comes from, this idea of entropy and cross entropy, right? If you're familiar with machine learning, you've probably heard of cross entropy. And the KL divergence is literally just the cross entropy minus the entropy of P. So you have your 2 distributions, P and Q. The cross entropy is H, P, Q, and then H of P. So this is the entropy of P, and then this is the cross entropy of P and Q, and then this is the relative entropy from P to Q, right? So these all come from entropy. Okay. There's 5 kinds of entropy, guys. There's a lot of entropy. That's why it's confusing, because there's thermodynamic entropy, there's entropy in classical statistical mechanics, there's entropy in quantum statistical mechanics, there's entropy in information theory, and then there's also algorithmic entropy, right? So there's kind of an overloaded term here in entropy. And we specifically, or at least the entropy that is referenced here in relative entropy with respect to the KL divergence, is this first one here, is this, or not the first one, the fourth one, entropy in information theory, right? Here it is. H equals negative sum over all these i's in X of pi times log pi, right? Where P is from some probability distribution on the set of X, right? Okay, so maybe let's go a little deeper. So entropy actually in information theory comes from Shannon, right? This guy, you've probably heard about this guy. Shannon developed what became known as information theory, a branch of science that underpins computers and so on. At the core of information theory is a measure of information called entropy. According to one story, the name arose from a conversation with John von Neumann, who advised him to use entropy for 2 reasons. First, a similar concept existed in physics. So John von Neumann was kind of a polymath, right? This guy like kind of was God mode at a bunch of different things. But John von Neumann actually told Shannon, hey, this idea that you have of this measure of information, there's something similar in thermodynamics and classical statistical mechanics, which we call entropy. You should probably call it that. And in Boltzmann uses the term H in his H theorem to describe entropy. So why did Shannon pick the letter H for entropy in information theory? Probably because John von Neumann told him to read Boltzmann's book, which, or I don't know if it was a book, it might have been a paper, which used H. So that's probably why we use the H to describe this, right? So that's where the fact that we use H comes from. Okay. I think the best way to understand this idea of entropy in information theory is the fair coin flip versus biased coin flip, right? So let's say you had a fair coin flip, right? A coin that 50-50 chance is head or tails, right? What is the entropy of that coin, right? So let's say you're summing over all the possible states of this coin, right? So there's only 2 possible states for this coin. There's heads and tails. And each one has a perfect 50-50 chance of appearing, right? So the probability of heads is 50, 1/2. The probability of tails is 50%, 1/2. So that's where that 1/2 comes from, right? And this logarithm here, it doesn't actually need to be in base 2, but here it's convenient to do it in base 2 because you're doing log base 2 of 1/2, which is easy to calculate, ends up being -1, right? But the important thing here is, okay, you plug in for the 2 possible heads and tails, you plug in the probability of xi, you put it in there, take the log, sum over both of them, you end up getting 1, right? So a uniform probability, where uniform there refers to that there's an equal chance between both heads and tails, yields maximum uncertainty and therefore maximum entropy. Let's compare that to this, the entropy of a biased coin flip. So let's say you now bend this coin, and the coin is now 70% chance landing on heads, 30% chance landing on tails, right? Still the same, 70 plus 30 adds up to 100, the same way that 50 and 50 adds up to 100. But now, when you plug this in, right, okay, there's 2 possible outcomes, heads and tails, 0.7 times log base 2 of 0.7, minus 0.3 times log base 2 of 0.3. Look at this, you get 0.88. Right? So what the hell does that mean? What the hell does that mean that the entropy of this biased coin is lower than the entropy of this fair coin, right? So non-uniform probability yields less uncertainty and therefore less entropy, right? So entropy, as they put it here, is kind of a measure of expected excess surprise, right? So another way to think about entropy is like how surprising is it going to be when you're looking at this probabilistic system, right? So if your probabilistic system almost always lands on head, you're going to have a lower entropy. But something that's really random, like an actual fair coin that's 50-50, higher entropy, right? So I feel like that's, to me at least, the best intuitive and kind of like satisfying explanation of exactly what entropy is from an information theory standpoint. Okay. Now let's just for closure here, let's look at some other types of entropy. So algorithmic entropy, the entropy of a string of symbols is the length of the shortest computer program that prints it out. Kind of sounds a lot like Kolmogorov complexity, right? So let's go into this. We're looking at algorithmic entropy here, right? What is the smallest amount of information that can convey this message, right? Let's say you're here and you're trying to send a message to this guy, right? So this is literally where these guys came up with this, right? These guys were code breakers. These guys basically worked for the NSA and then the post-World War II, like Cold War environment where you're trying to send secret messages to some guy who's in West Germany and he's sending secret messages. Like, how do you keep those messages from being read? Well, you got to encode them, right? You got to encode them into some secret language, and then you got to decode it, right? So what encoding scheme are you going to use for that secret message? Well, if you really think about it, the best type of encoding scheme is one that accounts for the probability of each individual token within this string of letters, right? So if you have an equal amount of probability for each letter, then using the same amount of bits to encode each letter is the best way to do it. But if you know that the majority of the time you're going to be sending the letter A, right? The probability of the token A in this string of tokens is much higher than the probability of D, then actually, to be more efficient, right, to have the smallest possible amount of information that sends that, you actually only want to use 1 bit to encode A and then 3 bits to encode D, right? And overall, this will end up sending less bits, right? You'll encode your message into less bits than if you encoded it this way, right? So this is the kind of ideas that eventually led to this whole idea of information theory and information theoretic entropy, and eventually the relative entropy and the KL divergence. More frequent equals less bits. Yes, kind of. Okay. Now we have entropy in classical statistical mechanics. And this is kind of, when you say entropy to a random person in the streets, this is usually kind of what they're thinking about, is like entropy in physics, right? And then within physics, there's different types of entropy, but this one here, Boltzmann, who actually has this on his grave. I thought this was pretty badass. He has the equation right there with his little constant on his grave, but you can see that this is a lot of the same ideas here. Boltzmann realized that in any random process, the final arrangement of matter was more likely than the initial arrangement, right? So this is kind of where the second law of thermodynamics comes from, where kind of heat just dissipates out and the molecules in some gas always just get more random, right? This thinking allowed Boltzmann to connect the known concept of entropy to probability. This was a major shift in science and meant that the usual approach to understanding reality by defining properties like position, speed, weight, and physical things could now be recast purely in terms of uncertainty and thus information, right? So really the idea of entropy comes from this, almost like if you can go all the way back to the Carnot cycle, right? The beginning of like people trying to understand heat and the way that heat dissipates in gases, and why do gases fill the container, right? And like, why is it more likely that you find the molecules in this gas in this particular state than all of the molecules like pushing against the piston in this particular state, right? So those ideas of like heat, I forget exactly when this was like 1800s, right? Eventually trickled through John von Neumann, who then advised Shannon to look into that, and then Shannon kind of developed that. So like you can trace this idea of entropy all the way back to like the 1800s, right? When people were looking at heat. Okay. We've gone a little bit deep. So I just wanted to show this because I think this is a nice slide. So this is a picture that demonstrates the GRPO from DeepSeek. So you can see here, there's two parts to this GRPO. There's this first part here, which is the kind of the actual core of GRPO, right? And then you have the KL divergence, but this is like a image of that, which I think shows it pretty well, right? Where you have the beginning. So here with DeepSeek R1, right, we're dealing with a autoregressive large language model. So the large language model is consuming this sequence of tokens here, and then it outputs some sequence of tokens, right? And the way that GRPO and R1 works is basically you sample a bunch of different completions, right? You look at the rewards for each of those completions, you look at the advantages for each of those completions, and this is going to be the bulk of your signal that you're using to push gradients into the actual LLM that outputs these things here, right? But the KL divergence is between these outputs, right? So you can see that the KL divergence is literally, this is the P and this is the Q, or in this case, it's the policy and the reference policy, right? And you can see that the KL is literally just this minus this times the log of that, this minus this times the log of that, this minus this times the log of that, right? So this is a more visual understanding of how KL divergence is used in the R1 paper here. Okay. Let me sip some yerba mate. Daniel Hunter, don't you need a stop bit? So I think you're talking about this. Yeah, I mean, the stop bit would also be one of these, right? So one way to think about it is how often is the stop bit, right? If the stop bit is happening every sentence, then you probably want a stop bit that is a small amount of bits, right? But if your stop bit, if you're sending entire books over, you don't really ever see that stop bit until the end of the book, so you might as well have it be something very complicated, right? So any kind of, whether it's like start sentence, stop sentence, any kind of these special tokens, also the most efficient way to pick the encoding for each of those special symbols would be with this type of information theoretic ideas as well. Can you please explain the diagram again? Yeah, it's a little bit hard because it's like you kind of got to look at the exact formula while you're doing it. Let me slide it up here so that we can alt-tab between them really quickly, right? So now we can do this, right? So you see here, AI is the advantage. So here's the advantage right here, AI. And then this, so you see how they're summing over these. GRPO samples a group of outputs, O1 all the way to OG from the policy. So you have these OI, I equals 1. So you see these are all coming from the policy. Your policy is your neural net. Your neural net is consuming some input and outputting these outputs, right? So this is the neural net consuming the input and then outputting all these outputs, right? You have this clipping. Where's the clipping? I don't think they show the clipping here. But you see how you have your reward minus mean over STD? That's right here. Where is it? Min of this. Clip AI. There's your advantage. And then the minus beta KL is this. So you see how this minus coming in right here? And then the KL is between the policy and the reference policy. So the KL between pi theta, this here, policy model, and then the reference policy, pi ref, reference policy. So in between these right here, right? And you sum it. So this is the sum over all of them, right? You're summing over all these I equals 1 all the way to G, right? So that's what these are. I equals 0, I equals 1, I equals 2, equals 3, all the way to G. Does that kind of make sense? Okay. Let's go to here. All right, so we're investigating relative entropy, right? And we want to go deep. So let's go into the actual implementations. We're going to look at how relative entropy or Kullback-Leibler divergence, KL divergence, is implemented in a variety of different machine learning frameworks. So the first one we're going to look at here is JAX, right? JAX is basically the successor to TensorFlow. It's fairly popular, especially if you're doing some weird stuff. But JAX also likes to pretend that it's NumPy and SciPy, right? So one of the strategies that they use to try to get more developers to use JAX is to make it more approachable. And one way to make it more approachable is to use similar syntax to NumPy and SciPy, which are really popular in the data science community. So if you want to get a bunch of data scientists and machine learning people to use your stuff, rather than making it look like C, which was kind of one of the problems with TensorFlow, you kind of make it look like NumPy. So here you have KL_div, right? And it takes two things here. It takes this P array-like and Q array-like. So that's the P and Q, right? The original P and Q from this one here, right? P and Q, your two distributions. Okay, so what does it mean to have an array-like distribution, right? Like how the hell is a distribution array-like, right? Well, this is how a distribution is array-like. So this is an example from Wikipedia here. You have two distributions, distribution P, distribution Q. Distribution P is a binomial distribution. There's three possible values here, 0, 1, and 2. And each possible value has a different probability. So the probability that it's 1 is 0.5, the probability, or not 0.5, but close to it. Probability that it's 0, probability that it's 2. Distribution Q is a uniform probability, uniform there because all three possible outcomes are have equal probability, right? So how would you represent these two distributions as an array? Well, this is exactly how you would do it, right? You would create a tensor that has the probability of each of these outcomes inside an array. So this is an array of size 3, right? And that's what these functions, that's what this special KL div is expecting that, right? So remember in our coin flip, you see how there's 2 here, right? Because there's 2 possible outcomes for this coin flip. For these distributions here, there's 3 possible outcomes, right? So that summation would be over the 3 possible outcomes there. Okay. So if we actually go into the KL div, right, we see that this is the actual Python function here, right? So KL div, here you have it. Here's a nice little doc string. And then you have this promote args inexact. And then it calls relative entropy. So actually, if you go deep enough into JAX, they stop calling it KL divergence and they call it relative entropy, which is, I think, the better name for it, right? But this promote args inexact, what is that actually doing? It's ensuring array-like outputs, preventing specific data types, excluding PRNG keys, right? So one of the things that JAX has that kind of makes it stand out is that it's very particular about the randomness in it, right? So like pretty much anywhere that you can have randomness in JAX, you have to feed it this random key, right? So whenever you're using JAX, you're constantly passing around these keys that allow you to kind of have fully repeatably random behavior, right? Because in any kind of differentiable computing problem that you're doing, you might have some randomness in there. You want that randomness to be repeatable, right? You don't want to have actual randomness in there. You want to be able to reproduce your experiments. So this KL div, the first thing it does is it checks to make sure that these are the same size, checks to make sure that they're right data types, check to make sure that each of the individual things are right, checks to make sure that your random keys are set up properly. So this is just kind of like a bunch of checks, right? A bunch of like generic checking stuff. Okay, let's go deeper. What is this rel entropy, right? So we went from KL div into the rel entropy. Now let's go into the actual rel entropy. This is the actual JAX code that does this, right? And you can see here, here's that same promote args and exact, but then there's this kind of weirdness. What's going on here, right? You have this bitwise and, you have the P and the Q, right? And you're replacing anywhere where both GT0 mask, replacing P with 1, anywhere where both GT. So why do we have this safe P and this safe Q? Like what exactly is going on here, right? And the reason for that is that the KL divergence is kind of fragile, right? Because of the way that this is formulated, right? Even just the simple problem of you're dividing by a thing, right? So if this Q of X is 0, now you have a divide by 0, right? So when you're actually writing the code that is going to calculate this, you need to make sure that the Q is greater than or equal to 0, right? So that's what these JNP wares are doing, right? That's why you have to make this safe Q, safe P. You have to make sure that there's not zeros or infinities or weirdness there, right? So the actual KL divergence or relative entropy is right here, right? X log X save P, and then X log Y save P save Q, right? So that's literally the formula. But all this other stuff here is just basically making sure that you don't have some situation where Q is 0 or P is 0, and you're just replacing all the places where P and Q are 0, right? So let's say that your distribution Q, these two here were 2/3, 2/3, and then you had like 0 for this column here, right? That's what this is checking for. Okay. How's it going, guys? How's it going, Julien? Let's look at this article here. So this is a blog post on John Schulman homepage from 2020. John Schulman was one of the original OpenAI guys. He now works at Anthropic, but he had this post here, approximating KL divergence, right? Pretty good post, recommended. Our options for computing KL, or relative entropy, depend on what kind of access we have to P and Q, the two probability distributions, right? We'll be assuming we can compute the probabilities or probability densities P of X and Q of X for any Q, right? So what he's saying is we can get these numbers. We can get this 9 out of 25, 12 out of 25, 4 out of 25, right? We can get those numbers, okay? But we can't calculate the sum over X analytically. Why wouldn't we be able to calculate it analytically? Computing it requires too much computation or memory. There's no closed form expression. We can simplify code by just storing the log prob, not the whole distribution. This is a reasonable choice if KL is just being used as a diagnostic. Okay. The most common strategy for estimating sums or integrals is to use a Monte Carlo estimate, right? And I have here two pictures that kind of show you how Monte Carlo estimates work, right? Monte Carlo estimates are basically saying, in this case, we want to approximate the number pi, right? How would you approximate the number pi? Okay, well, how about you draw a circle, or in this case, a quarter of a circle, and then we're going to randomly sample points inside this. And then we're going to look at the ratio of the points that are inside versus the points that are outside. And you can see that as we increase the number of samples, n, here, from 5,000 to 30,000, the approximation that we get for pi using this kind of numerical sampling Monte Carlo-based technique gets closer and closer and closer to the real number of pi, right? So what he's saying here is, for this type of distribution, it's pretty easy, right? Like there's only 3 possible values here. We can get the exact probability for each of these 3 possible values. We can do this sum, right? The sum from I equals 1, in this case, to 3, pretty easy to do. We can just calculate that. But for a lot of real problems, that probability distribution is not going to be that easy to do. So we're going to have to approximate KL divergence or relative entropy using the Monte Carlo technique. He goes through this whole kind of derivation in the blog post, but ultimately the most important thing here is this, right? This is the actual approximations that he ends up using, r log r minus r minus 1, and then r minus 1 minus r log r, where r is the ratio between P and Q, right? P over Q. And you can see that that's actually what is being calculated here. So you have rel entropy PQ minus P plus Q. So the actual implementation in JAX is basically one of these approximations. Okay. Numerical stability issues. Random question. Do I have any cats from Nods? Oh, yeah, I do have a cat. I have a white Bengal cat that looks like this. Looks like this one. That's why there's cats everywhere on my YouTube channel. It's because I actually have a cat. The cat is called Boo. She's made an appearance on several streams, but she's a little bit shy. Okay, let's go back down to here. We were talking about numerical stability, right? Okay, so division by 0. When Q is 0, this division by 0 here, this is going to explode, right? So you can't deal with that. KL divergence becomes undefined. Logarithm of 0, when P is 0, taking the logarithm of 0 leads to a negative infinity, right? So P is also, you can't just take log of P if P is 0. In some cases, and this is the numerical stability, KL divergence can become very large, leading to overflow issues. This can happen when the difference between P of X and Q of X is significant. This can be mitigated by using log probabilities and appropriate scaling techniques, right? So maybe let's start here, right? So what is this issue that they're talking about? Let's say you had a tensor in Torch, right? So you have these numbers here, 50,000 and negative 50,000. We're putting this inside a float 16 data type, and then we're doing the log softmax, and then we're doing the KL div right here, right? When you do the KL div in this precision of float 16, look at this, loss value infinity, right? So that's what we mean by these numerical stability issues, right? Is that if these numbers get too big or too small, you can start having issues. And the too big or too small depends on the data type itself, right? Because at the end of the day, inside your computer, these numbers are represented using these data types, right? And the data types, such as float 32 versus float 16, have a different number of exponents. You see this exponent, right? So this kind of determines how big and how small the number that you're using can represent, right? So like with an exponent of 8 bits, you can represent 1 times 10 to the 8, or you can represent 1 times 10 to the negative 8, right? So you can represent 0.00000001 or 1 with 8 zeros after it, right? And you have 1 bit for the actual sign, whether it's negative or positive, right? If you had an unsigned float 32, it would not have this sign bit, right? That would allow you only to represent positive numbers. And then this fraction is kind of like the precision of the number, right? So like 0.0000012345, like all the way to that, right? But the problem is that in these kind of, especially with something like a language model, right, you're going to get very, very small numbers and very, very big numbers. So let me just show that real quick here, right? So this is something that I have shown before, but this is kind of a visualization of a transformer-based language model, right? And you can see that it's consuming these tokens here, and then it's outputting a probability distribution over all possible tokens, right? So the probability distribution over all possible tokens is a fancy way of kind of saying, what is the probability that the next token is this versus this versus this versus this versus this, right? And the length of that, or the number of possible values or tokens, is the vocabulary of the language model. And the vocabulary of the language model can be like 100,000, right? So what your model is outputting is a probability distribution over 100,000 possible values, right? So now you can see how this gets out of control, right? Because here, this summation here is only over 2 possible values. There's only 2 possible values in a coin flip, right? In these distribution here, there's 3 possible values, right? Now imagine doing that with a language model where you have like 30,000 possible values. A lot of those values are going to have extremely low probabilities, right? So like the probability of the next word being volcano is like 0.00000001, right? So then when you're doing these summations or these multiplications here with that you need to do, you're going to end up with these really, really small numbers. And eventually you're going to end up with these kind of numerical stability issues just because the way that these numbers are represented inside computers is just too small, right? So we're going to use logs. Okay, in statistical modeling and machine learning, we often work in a logarithmic scale. There are many good reasons for this. When x and y are both small numbers, multiplying x times y may underflow. However, we can work in logarithmic scale to convert multiplication to addition, right? So logs have this magical property where the log of x times y is the log of x plus the log of y. And there's a kind of a similar situation when you're taking the derivative. So here you're taking the partial derivative with respect to x of f of x, of log f of x times g of x is the same thing as taking the partial derivative for each one individually and then adding them together, right? Differentiating each function separately is easier than applying the product rule, right? So because of these properties of logs, it's going to be easier to work with logs, right? You can turn any multiplication inside into a addition, right? And in this case, this also works with x over y, right? So imagine x times 1 over y, or x over y is the same thing as log x minus log y, right? So that's exactly what we have inside our relative entropy equation, right? We have, where is it? Right here, right? We have f1 over f2. We have the log of f1 over the log of f2. In order to do that, you can just say log of f1 minus log of f2, right? You can replace that with that, and that helps you simplify this entire situation. Working in the log scale is also more numerically stable than many standard libraries. And here's some pictures to show you why that's the case, right? So here I have a plot of log base e to the x. And again, the base for the log doesn't really matter, right? It can be log base 2, log base 10, log base e, like it all kind of works out the same anyways. But the important thing here, right, is that if you plug in a value of x equals 1, and let's say you have this line y equals x, you're going to get 1, right? If you plug in a value of x equals 10 million, you're going to get 10 million, right? So like this grows very quickly, right? So you can very quickly get very, very big numbers or very, very small numbers with this type of relationship. Y log of x, right? The log smooths out. So you see how this is kind of smoothing out? So basically the high level intuition here is that no matter how big you make this x, right? If you plug in x equals 10 trillion in here, it's never going to get as big as this, right? So the log kind of naturally smooths out, right? Like you can keep increasing x exponentially. You can keep increasing or making x smaller and smaller and smaller, and it's just going to have a nice value, right? And that's why people use log, because of these properties and because of this kind of numerical property. Right, you guys have probably seen this here, linear scale, logarithmic scale, right? Linear scale kind of quickly gets out of control. Logarithmic scale allows you to kind of flatten that out. Are people following? I don't know if people are following. I'm not seeing any questions. Okay, so we were here. We were looking at the implementation of KLDiv in JAX, right? We went into the KLDiv. There's the wrapper here for type checking. Then we went into the actual implementation here. But we're still stuck here with this x log x and x log y. Like, how is that actually being calculated? So let's go one level deeper. And if we go one level deeper, we're going to end up in CUDA, right? So depending on where you run this, right, when you're writing this Python code, this JAX Python code, that's not actually what's running, right? What actually ends up running on your computer is going to be lower level than that. If you're running on a CPU, your operations are going to be implemented using standard libraries, such as libm and mkl. If you're running this on a GPU, you're going to end up with some CUDA library that's running it. And then the CUDA itself is probably going to have slightly different versions depending on what GPU you're running it, right? So different GPUs maybe have different specialized chips in there that allow it to perform some of these things. So if you have an older GPU, it might use this particular implementation of the log. If you do this other GPU, it might have this particular implementation of the log, right? It starts getting very complicated once you go down to the level, because in order to do something optimally, you have to be hardware aware, right? You need to know what the hardware is to run something more efficiently on it, right? So as you get closer and closer to the hardware, the different types of solutions kind of explode because there's a lot of different types of hardware, right? So this is I thought this one was kind of cool. This is not the standard library, so there is a log implementation in the standard library, but this is a different one. This is libquadmath. So this is for high precision data types, but I thought this was crazy. But in this particular implementation in GCC, they're basically using this to estimate the log. So log of x plus 1, you can kind of use this infinite series to approximate it. And this is the actual line of code. Series expansion of log 1 plus x. Like, just look at this. It's literally like, it's kind of like, sometimes you'll run into a meme where they're like implementing an is odd or is even function, and it's just this giant like if else statement of like, if it's 1 equals odd, if it's 2 equals even. And it's kind of a meme, but like if you dig deep enough into the implementation of log that runs on a CPU, in this case, this one would be running on a CPU. This is not CUDA code, but look at this. It's this giant nested, like whatever this is, 10 line that goes all the way to 14. So basically someone just arbitrarily chose, okay, once you go up to 14 of these terms, that's probably close enough. So that's what's actually running. Off topic, how would I learn more about the CPU CUDA dispatching logic systems? If you're interested in CUDA, there's like this website that what's it called? CUDA Python website converter or something like that. Let me see if I can find this. I'm never going to find it. But there's like this website that you can go to where they have like the algorithm in Python, and then as soon as you write the Python code, it shows you what the actual C code, and then even CUDA code, if you want to go there, is actually running. Visualizer website learning. I'm never going to find this, especially not under duress here. All right. Maybe one of you guys knows what I'm talking about, but I'll figure it out and I'll post it on the Discord. Okay. Let's go here. Actually, you know what? Why don't we test GPT? Let's test GPT. Let's close that. I remember a website where I could put my Python code in one side, and then it would show me the actual lower level code that is running on the other side. Do you know what this website is? Let's see if it can actually find it. This one. Boom. Look at that. That's fucking crazy. All right, here we go. This is what I wanted to recommend. So, Daniel Hunter, here it is, right? So, like, let's say you wanted a Python code. Where is it? Python. Here we go. Boom. Okay, so here's a little function. Define. Let me zoom this in. This is probably way too small for you guys. But when you write Python, right, that's not actually what's running on your computer. That's eventually getting compiled, right? Just in time. That's what Python does, right? It compiles it as it runs it, basically. And this is what's actually running. So when you do this, this is what's actually running. And you can actually, they have a version of this, I don't know how to get to it, but for CUDA as well. Let's see, compiler options. Do they have PyTorch? No. Python, what if I do this? No. Okay. Godbolt CUDA. There you go. CUDA. Where is it? C. CUDA C++. Okay. I don't know why this website just fucking exploded, but all right. Either way, use that if you're interested in CUDA. All right, let's go back to this though. So we looked at the implementation in JAX. Now let's look at the implementation in PyTorch, right? So we go to the PyTorch documentation and we find two different versions of KL, divergence or relative entropy. We find this NN functional KL div, and then we find this NN KL div loss, right? So a lot of times the KL divergence is used as part of some loss function, right? Where you have, here's your loss function, there's like 14 terms, and then there's also a KL divergence in there. So you have the loss version of it, and then you have the kind of more generic version of it here in the functional API, right? And if you actually go into GitHub and go to the actual PyTorch repo and type KL underscore, here are the three different versions here, right? So there's actually three here. There's the Python function in the functional, right? So that's this one, functional KL div. That's your KL div inside functional.py. Then you have the actual function, right? So this functional.py, that's not the real one. That's just the Python function. Then that thing will call the actual thing that's actually running, which is the CPP, right? Inside native loss.cpp. And then you have this other one, which we're going to discover here, this distributions KL.py, which is kind of weird. But okay, let's actually go into KL div, this one inside, and you can see that it calls right down there torch.kldiv. So like now you go to here. And then once you go into this one, this is the CPP. There it is, right? So exponent of target times target minus input, x log x of target and target minus target times input. So there it is, right? There's that relative entropy. There's that x log y, right? The same x log y, x log x that you see in JAX, right? So we found where it's implemented in PyTorch. But why is there this if statement here, right? If log target else. So that's because the PyTorch function, you can actually specify whether the targets are in log space or not, right? So why does PyTorch want log probs for input? So you can, the input here is already in logs, right? So PyTorch KL divergence function is designed to avoid repeatedly computing the log if you already have a stable log probabilities. Internally, it implements something like this, right? So if you already have it in log form, right, we can simplify the code by just storing the log prob, right? So you're already kind of using the log anyways. Your probabilities are already in log space anyways. So you don't need to undo it and then redo it. You might as well just have the KL divergence function be implemented such that it can take in and output in log prob space. Okay. This is the other one. So if you remember, we went into the PyTorch repo, we typed KL div, and we were looking at the different versions, and there was this weird one here, torch distributions KL.py. All right, so what the fuck is that? So let's go deeper into that. This is a version, and you can see that this is now no longer taking tensors or array likes, right? Now P and Q are no longer this tensor of probability distributions. Or probability values. It's instead this distribution object, right? So this comes from this torch distribution package, which contains parameterizable probability distributions and sampling functions. It allows the construction of stochastic computation graphs and stochastic gradient estimators for optimization. Okay, so basically it was a ripoff of the TensorFlow distributions, but it's just like this kind of object-oriented mess where everything is a distribution object. You have a bunch of different types of distributions, and you can see what actually happens here is that it has this dictionary, right, of that is the key for this dictionary is the type of this distribution, right? So this distribution type, there's a bunch of kind of child types that inherit from it, and then you're looking at those and then saying, okay, well, if P is a Gaussian distribution and Q is a uniform distribution, then we're going to use this specific version of the KL divergence. And then you look at this kl.py file, and it's literally a bunch of different implementations of KL divergence depending on which type of distribution it is, right? So you have your KL for two beta distributions. You have your KL for binomial and binomial. You have your KL for Dirichlet and Dirichlet. You have your KL for categorical and categorical. So this is kind of just the most ridiculous implementation I've seen, because it's literally like the implementation of KL divergence is a dictionary containing a bunch of different implementations of KL divergence depending on the type of distribution that you have. So I don't know. You peel back the layers of the onion, and eventually you end up in some kind of spaghetti code mess, which is kind of always the case, to be honest. All right. TensorFlow documentation, TF Keras metrics of KL divergence. But here's the reality of TensorFlow, guys. TensorFlow is dead. All right. So here's a chart. This comes from Papers with Code. But you can see here, this is December 2014, and this is now December 2024. And this shows you the share of implementation. So in Papers with Code, right, they're constantly ingesting papers into their database. And for each paper, usually they have some accompanying GitHub repo. They look at that GitHub repo. What machine learning framework is that GitHub repo using? And you can see that over time, right, initially, it was all this light blue, other languages and framework, I guess. And then you can see here, look at this. TensorFlow is this orange. So 2015, 2016, 2017, 2018. So the peak of TensorFlow was 2018, right? Which is actually, that's when I was at Google around this time, right? 2017, 2018. And that was, I remember that when I was there, they had the TensorFlow 2 like release event. So like that was basically peak TensorFlow, 2018. But you can see that over time, this TensorFlow has actually died out, right? So you can see that like less and less and less and less and less people use TensorFlow. And it's actually kind of like a meme at this point that like no one uses TensorFlow. Even within Google, you're going to use JAX. And there's people that actually use PyTorch within Google, which is kind of weird to think about. But the big one is PyTorch, right? This is this darker orange here. It kind of just keeps growing in market share. OpenAI uses PyTorch. X uses PyTorch. They all use PyTorch. Even JAX is not picking up much. Yeah, JAX is just like, it's definitely way better than TensorFlow, and I think in many ways it's actually better than PyTorch, because it's like PyTorch. The problem with PyTorch is that there's so many people that use it that there's like hundreds of people just constantly pushing crap into PyTorch, and there's lots of different requirements from lots of different people. So anytime you have a code base where there's just so much inflow and so many people using it, it kind of ends up kind of spiraling out of control, right? You just have so much cruft. There's so many special cases that it kind of starts to accumulate this garbage, and it just becomes very difficult. It's kind of what happened to TensorFlow, to be honest. TensorFlow kind of had the same Achilles heel, where it's just like there was so much shit going on that it just accumulated a bunch of crap and then became unusable. And PyTorch is kind of like dancing that line, but JAX, because it's relatively new, it's kind of clean, you know, and that cleanliness is kind of refreshing. So if you want to write something, some kind of differentiable computing idea that you have, I feel like JAX is probably the best way to do it. But if you want to make a big company, or if you want to use somebody else's stuff, it's probably going to be PyTorch. How's it going, Majetti? All right. So we looked at a bunch of different implementations here. We looked at the JAX implementation. We looked at the PyTorch implementation. We looked at the TensorFlow implementation. And now just for fun, let's look at the TinyGrad implementation, right? So TinyGrad is kind of a newcomer here in the machine learning framework world. This is a machine learning framework created by HOTS, right? And you can see here that TinyGrad is basically just Python that wraps C, right? And Python is C, right? If you really want to know, Python itself is kind of just basically C with a nice little like wrapper on top of it. But I was trying to find it, right? I was sitting there and I was like looking at the TinyGrad code, looking at the TinyGrad documentation. I couldn't find it. Here's binary cross entropy. Here's sparse categorical cross entropy. I was like, where the fuck is relative entropy, KL divergence, right? I was like, where rel entropy, where KL divergence, right? I looked in the issues, the pull request. Maybe someone submitted it as a pull request, but it never got pulled in. Like, where is this? This seems like such a basic thing. Like, how can you have a machine learning framework that doesn't have KL divergence in it, right? And then I realized that actually you don't really need it, right? And here's a little snippet from O1 Pro. When you compute a loss based on predicted probabilities versus ground truth one-hot labels, which is cross entropy, which is basically what large language models are using as a loss function, the KL to divergence from a one-hot to a predicted distribution of Q, right? A one-hot is this thing here, right? So one-hot vector is a vector where it's 0 for everything and then 1. And why are you using one-hots when you're training language models? Because what you're using to push the gradient into the model is cross entropy, and this cross entropy is basically saying, okay, what is the word that actually appears after this sequence of input words in the actual data that I'm using to train this, right? So I'm sampling some batch of data, which is some cleaned version of the internet, and then in that specific sentence on that specific batch that we got from the internet, what was the actual word that came after data visualization empowers users? And then that's going to be your ground truth one hot, right? And then you're basically just doing supervised learning and cross entropy, push it all the way back. But here's the important part here. Often we focus on minimizing cross entropy. Minimizing cross entropy is essentially the same as minimizing KL divergence plus some constant. Ah, we already knew this, right? We already knew this. Let's go back up here. Here we go. KL divergence between P and Q is just the same thing as the cross entropy between P and Q minus the entropy of P, right? So if we're trying to do this DeepSeek R1, right? Isn't this kind of just a constant, right? Let's go back up here, right? This part here, this H of P, do we really need that, right? Couldn't this KL term here, couldn't this KL term right here, couldn't we just have that be the cross entropy? Do we really care that much about this term here? And that's when I finally understood, why does TinyGrad not have an implementation of relative entropy or cross entropy? It's because it's the same thing, and because TinyGrad's all about lines of code, guys. So famously, TinyGrad, most code collapses under its own weight. The complexity becomes too much to keep making progress. Line count is imperfect, but regardless of metric, TinyGrad is 2 orders of magnitude simpler, right? So you have your famous meme lines like, I purchased the siren in the office. If TinyGrad goes over 5,000 lines, it will go off. So there's this weird obsession that George Hotz has with reducing the total lines of code in the TinyGrad code base, right? So if you're really, really trying to reduce the total amount of lines of code, then one easy way to do that is that rather than having a separate KL divergence, which is basically just calls this cross entropy minus the entropy, just use this cross entropy, right? So now I finally understand why they don't have it. It's because you could just use cross entropy to do it. I still feel like that's not necessarily a great design. I kind of prefer, even though it's more kind of verbose and kind of more cluttered and definitely adding a lot more lines of code, I think that there's something to actually having explicit versions of these rather than just kind of assuming that whoever is using this is going to be like, okay, I kind of want to have some kind of KL divergence type thing. I can just use the cross entropy instead of KL divergence. But Heuristics AI, how's it going? All right. That is all I have. What time is it? 11:04, really only 1 hour, so I feel like I kind of blasted through this, but I think it was maybe a little bit too arcane for most people. I don't know. Let me sip some yerba mate. We'll do a summary. If you guys have any questions, it doesn't actually even need to be a question on relative entropy. If you guys have any questions about R1 or superintelligence or whether I have any cats, like, feel free to ask that as well. Everybody's tired today. Relative entropy. Here's the summary. Relative entropy is something that comes up in a lot of machine learning papers, especially reinforcement learning papers, right? Where you're dealing with these policies, these models, these neural nets that are outputting some probability distribution over a set of possible actions, next actions, or in this case, tokens, right? Which token am I going to output next? Which of these tokens comes next? And relative entropy is a way of a distance metric that allows you to say how different is this distribution P from this distribution Q, right? Or how different is this neural net, which is outputting some probability distribution over a set of tokens, to this probability over the set of tokens that this other neural net outputs, right? Maybe it's an older version of your policy. This is a slightly newer version of your policy. Maybe this is the human versus this is like a human operating a robot versus this is the neural net that you have trying to learn the human, right? Imitate the human. KL divergence comes from these kind of code breakers, right? So this post-World War II kind of information theory renaissance that happened with Shannon and von Neumann. Well, two of those guys were Kullback and Liebler. Unfortunately, they were probably, pretty old-fashioned in their views, and they decided to call it KL divergence instead of relative entropy because they really wanted to force people to remember their name, right? They're kind of into this vanity ego thing. But I prefer the name relative entropy, so I'm advocating for people to start using rel-ent instead of KL divergence, because KL divergence doesn't help people understand, and we're in the business of trying to help explain or understand the idea. Okay. Is the policy generated text versus expected text? No, the policy is a word used to describe the neural net. So the policy is a model, right? So you see here, policy model. So the policy is just a neural net, and the neural net is parameterized by some parameters, right? So you know how when they say llama has 70B parameters, 70B is the number of this theta, right? So there's 70B, this theta is 70 billion numbers. In a llama 7B, this theta is 7B numbers. So a policy model, DeepSeek R1 policy model is some neural net parameterized by these numbers. And that policy model is going to consume a sequence of tokens, right? So it's consuming this red, then 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 this red. And then it's going to produce this green, green, green. It's autoregressive, right? So it's basically just, as soon as you're here, then you can make the next one, 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 right? So that's what the policy is. It's just a neural net. Why is the constant HP ignored or unimportant in calculating the KL when approximating to cross entropy? It's not necessarily unimportant. It's just that it's less important, right? So as they're saying here, right, minimizing cross entropy is essentially the same as minimizing KL divergence plus some constant, right? So if you minimize cross entropy, it's very similar to minimizing, right? If you're minimizing this HPQ, it's kind of the same thing as minimizing DKLPQ, right? It's just that you also have this HP, but if this entropy of P is kind of like a number that doesn't really change that much, then it doesn't really matter, right? You're minimizing this is kind of the same as minimizing that. That's kind of what they're saying, is that it's kind of the same, but it's not actually the same, right? You would, if you actually calculated the entropy of P, there's probably some signal in that, right? Because as we said before, the entropy changes depending on the probability distribution, right? So if you take a coin flip, and the coin flip has a 50% chance of every single possible outcome, that has a higher entropy, right? So this value here, this H of P, depends on the entropy of the actual policy, right? So if your policy is out, look at this here, right? So you can think of this like this is the probability for each token, right? Your policy is outputting, in the DeepSeek R1 paper, the policy is a language model that's outputting a probability distribution over all possible tokens, right? So you can envision a world where that probability distribution over all possible tokens is very spiky, right? Like if there's basically 3 tokens that have a high probability and everything else is 0. That's going to have a different entropy than if you have a very uniform probability distribution, right? Imagine a probability distribution where every single token has an equal chance of being selected, right? In that case, the difference between that kind of more uniformy versus the kind of more spiky probability distribution would mean that this value is different, right? This h of p is going to change depending. So in that case, minimizing cross entropy and minimizing KL is slightly different, but at a high level, they're kind of the same. What's entropy? Well, actually, good question. Entropy, there's a lot of different types of entropy, and the entropy that we specifically talked about today is entropy in information theory, which is labeled H. And the reason it's called H is because Claude Shannon was working under John von Neumann, and John von Neumann, being a very cultured and well-read polymath, was aware of Boltzmann's work, and Boltzmann, who's this like German guy who lived in the 1800s, he did a bunch of work that kind of built on top of the Carnot cycle and kind of like the heat engines work, right? So people who were thinking about gases and pistons, right? Like you're talking about the beginnings of the steam engines, right? Whenever people were like, hey, if I heat the gas in this piston, the molecules push up against the head of the piston and it pushes that. Like how the fuck is that working, right? And they started thinking about kind of the probability of particles. And Boltzmann, in his particular theory around that, called this entropy, or I don't know if he actually coined the term entropy. I think one of the earlier guys did, but he used the letter H, and that's why John von Neumann pointed Shannon to that work, and that's why Claude Shannon, who is the guy who's kind of credited for information theoretic entropy, decided to use the letter H. So that's what entropy is. Okay. And then once we kind of went into entropy, then we also looked at a couple different implementations of KLDiv. We looked in JAX, and we traced it all the way down into the actual CUDA code, right? So you trace it down further, and then you go finally get to this x log x, and then that x log x, eventually at some point you hit the standard library implementation of log, which are usually based on some kind of like expansion series like that. And then here's the actual atrocious line of code that people end up using, right? So right here, this is when you type log of x, at some point, you're eventually getting down to this line of code right here. Not this one specifically, because this is a slightly different library, but something like that, right? Some kind of expansion or approximation. We looked at PyTorch's implementations. We found this kind of crazy distribution implementation of KL divergence, this kind of object-oriented implementation where you have this dictionary of a bunch of different implementations of KL divergence depending on which distribution you're using. We made fun of TensorFlow dying and PyTorch kind of gaining increasingly larger mind share. Right? So this is 2014, 2015, all the way to 2024. This orange is TensorFlow, so you can see like over time, this is probably the peak TensorFlow, and then it eventually died off. And then here you have PyTorch just kind of increasing. And I even though JAX feels like no one's using it according to this, I still feel like it's a very clean. It's more pleasing to use JAX than it is to use PyTorch, to be honest, because it's a little bit more functional. PyTorch is more like OO. And then we finished it with TinyGrad, right? And I was sitting there trying to find KL divergence or relative entropy in the TinyGrad documentation inside the TinyGrad pull request and the issues. I was like, why has no one used this? Right? This feels like it's such a basic thing. And then we kind of realized that the reason it's not implemented there is because you can effectively use cross entropy, and because they're so obsessed with lines of code that pretty much they're just going to have one implementation. It's going to be cross entropy. Oh, you want to minimize KL divergence? Minimize cross entropy. Oh, you want to minimize this other kind of variant of entropy? Minimize cross entropy. So it's like the lines of code means that if you tried to implement this in TinyGrad, you would not be able to implement this KL divergence, but you would be able to use the cross entropy here. How's the reward calculated? So you're talking about in DeepSeek R1, this reward here. So here they have RM, which stands for reward model. And basically what the reward in reinforcement learning is coming from the environment, right? So if you have a robot in a simulation, or let's do something simpler. If you have a game of Go or a game of chess, right? At the end of that game of Go, someone's going to win, right? So one way to do it is say, okay, well, if you win this game, then all the actions that you took up into this game, right? The move right before you took the winning move, and then the move right before you took the winning move, and then the move before the move that you took the winning move, right? All those moves are going to have a high reward. And then if you look at the person who lost the chess game, you can say, okay, well, the move before they lost is probably bad, and the move before the move that they lost is also probably bad, right? So any environment where you can have a reward signal like that, you can create these reward models, or you can have this idea of a reward, right? Where you can then say, okay, well, this entire trace here is good things, and this entire trace here is bad things, right? And normally this only works for things like robots in simulation or games where you have a winner and a loser. But what's popular now is doing this with math and coding, right? Where in math and coding, you can have this long sequence of tokens and eventually get to a final answer. And is that final answer correct, right? You can verify that that final answer is correct or wrong, and then use that to get this idea of a reward, right? So you can look at, okay, here's the beginning of the math problem, and then here's 4 different kind of traces outwards from the beginning of the math problem. Which one of these actually gets it right and which one of these gets it wrong? So if you know that this one is right and this one is wrong, then you can kind of go all the way back and say, okay, well, all of these ones are probably wrong, right? In DeepSeek R1, are they using online RL or offline RL? Okay, so what Ed is talking about there, online and offline. So these policies, right? When you're using a neural, when you're doing reinforcement learning, you're pushing gradients into a neural net called the policy, right? And sometimes, especially if you have a large distributed system that is a bunch of GPUs that are all playing different games of AlphaGo, right? The data that you're collecting, right, is not the same as the neural net that you have anymore, right? So the neural net policy that created this specific game is different from the neural net policy that you have right now, right? So is it weird to put, it's hard to push gradients into a neural net that wasn't the neural net that created that, right? So online versus offline RL is more, are you pushing gradients directly into the neural net that actually created this exact experience that you're pushing gradients from, versus offline RL, it's like, hey, I just have a bunch of data that was created by a policy that's different than the policy I have now, but I can push gradients into that, right? So online versus offline RL, online RL, it's like the policy that you're using is relevant because it's like literally the policy you use to collect that specific piece of experience. But in offline RL, you have a lot more data available, right? Because you can use thousands of games from other policies that weren't even the ones that you're pushing the gradient into, right? And in any kind of distributed RL system, you're running into this problem constantly because your policy, as soon as you push one gradient, then all the other policies that you're using to do your actual experience collection are now old, right? So this policy pi old, that means that like, okay, you pushed a gradient. Now the policy that you're using is different from the policy that you had before that collected that experience. So is DeepSeek R1 on policy or off policy? I think it's off policy, right? And that's why you have this KL divergence here, right? So usually in a lot of RL, this KL divergence is basically trying to say, okay, this policy is different from the policy a couple iterations ago, and I want the policy from a couple iterations ago and the policy that I have now to be kind of similar, right? I don't want the policy that I have now to drastically change from the policy that I had 4 steps ago, right? Because say the policy that I have now is going to be kind of optimized for the things that I just recently pushed into it, versus the policy that I had 10 steps ago is more optimal for the things that were pushed into it at that time, right? So by using this KL divergence, this relative entropy, as part of your reward or your loss function, you're basically preventing the policy from drifting too far and kind of over optimizing for the exact experience that you happen to have pushed it at this iteration, right? Here's a better explanation. The algorithm performs iteratively. At the ith iteration, we use the current model pi theta I as a reference model and optimize the following relative entropy regularized policy optimization problem. See, so relative entropy regularized. So relative entropy regularized, another way of saying that is KL divergence is regularizing to prevent the policy from drifting too far, right? So relative entropy is regularizing the policy. So pi theta, we want pi theta to maximize this reward R, but we don't want pi theta to be very different from pi theta I, right? So we want it to improve based on this new data that we got, but we don't want it to drift too far from where it was before. The reward evaluator is the replay buffer. So the replay buffer basically refers to the experience. So like whenever you're doing reinforcement learning, you're collecting a bunch of experience, right? You're playing a bunch of games of Go, and then you're storing those games of Go in some database, which is called the replay buffer, right? And then whenever you're pushing actual gradients, you're sampling some group of these outputs, right? So you're saying, okay, here's 10,000 games of Go, and I'm going to pick 100 of those games of Go and then use that to push a gradient, right? So you're sampling from that. So the replay buffer is the effectively bucket that contains all the data that you're collecting and putting into it. In math reason probs, we deal with out of distribution generalization, OOD. When getting to next step in solving math problem, language model may not have seen it in training data. How DeepSeek or RL in it handles this? So DeepSeek is a neural net, right? So at the end of the day, all this neural net is doing is it's outputting a probability distribution over tokens, right? It's just giving you, here's the probability that the next word is this, here's the probability that the next word is this, here's the probability that the next word is this. So you don't actually know which of those sequences of next words is going to take you to the right answer, right? And that's really what DeepSeek is trying to solve, is saying, is this sequence of next tokens taking me to the right answer? Or is this sequence of next tokens taking me to the right answer, right? And the only way to do it is to just try it out, right? So what these completions are, it's basically different paths down the tree. And I think I would recommend the stream that we did last week if you want to understand this idea of like trees and the tree of knowledge, and like the fact that what these models are doing is they're kind of trying out different paths down this tree, and then you're kind of evaluating using a reward model to which of these trees was the better choice. And then once you know which one was the better choice, then you basically wrap it all up and push a gradient based on that. So it's question from Ed. So it's not like self-learning then, because you need to collect the preference data before doing the RL data, the RL tuning. So self-learning is like a pretty broad term, right? So like I would say it is self-learning because it's collecting its own experience, right? So like in RLHF, right, reinforcement learning from human feedback, the way that you're getting this reward signal is from a bunch of human examples, right? So it's almost more like supervised learning. You're basically saying, here's the question, and then here's the human answer that we want, and then here's the human answer that we don't want, and then we're just going to push a gradient based on that, right? But so like I wouldn't call that self-learning, because you're using this RLHF dataset, which was created by humans, right? The human feedback. In this case, in DeepSeek R1 and in KimiK 1.5, the reward is coming from the environment. So it's not like DeepSeek R1 is like learning in the sense that it's like creating. Well, it is learning in that sense because it is creating its own traces, and then you're using the environment reward signal to determine which of those traces are the best, and then using that to train the DeepSeek R1. So it is self-learning in that it's exploring the tree of knowledge, and then you're using the fact that for something like math and code, you have the ability to take those explorations or those reasoning traces and label them as either good or bad, and then using that to collect more experience and then train push gradients, and then use that new policy to go out and explore more trees, right? So it is kind of self-learning in that way. But self-learning can mean like pretty much anything. I could make the argument that like everything is self-learning. Reinforcement learning? I don't know what you're trying to say. Oksuk. All right. Federated learning folk and mobile folk uses TensorFlow. Yeah, TF Lite is still popular for TensorFlow Lite is like the models that you use for running on like a cell phone. So like I remember actually doing that. I remember writing shit in PyTorch and then compiling it so that, or not compiling it, but basically modifying it so that you create this TF Lite and then run that. That's the actual model that you run. So you're developing in PyTorch, but then you're creating a model object that is a TF Lite model, and then that's what you're actually running on the mobile device, right? So in that case, TensorFlow was literally just only used for the kind of inference on the actual device. But I think even for that, there's other more popular things now. Like there's this ONNX. This? Yeah. ONNX for TF Lite. Yeah, here you go. I think this might be the exact pipeline that I used. So you have some model that you wrote in PyTorch, that you trained in PyTorch, all your code is in PyTorch, and then you use this ONNX open neural network format to basically put your model in such a way that it can be run by TF Lite. Because TF Lite is what's actually going to run it on your cell phone. But I don't know. Long term, I feel like PyTorch beats TensorFlow, and I think the data supports that. Why is OpenAI so far behind? I don't think they're far behind. I think people got surprised by R1 because it was very good. But, you know, there's the positive of releasing your research like this is that everyone can use it. The negative of releasing your research like this is that everyone can use it. So you know for a fact that Noam Brown and all the different people at OpenAI read this DeepSeek R1 paper and they were like, oh, okay, yeah, that's cool. Okay, we're going to do the same thing, except we can do this with a 10x training budget because we have 10 times more money. So if anything, OpenAI benefited from DeepSeek R1 being released because now they can take all the ideas that worked and then just apply it to their stuff. Thoughts on R1 versus Pro Mode? I think Pro Mode still edges out R1, but R1 is really good for the size and the fact that it's open source. It's pretty crazy. All right, let me see if there's any more questions here. What's your take on Project Stargate? So there's like this BG2 podcast. These guys. So if you're interested in that kind of shit, I would recommend these guys. These guys are two like VC money guys, and they recently did a podcast on the Stargate. And these guys, they're like finance bros, right? So like they've been in that world the entire time, so they understand, right? And the way that they actually said it is that they agree with Elon, right? Where they don't actually have $500 billion. Like it's kind of like they're taking out a loan on a loan on a loan of a thing. And like, you know what I'm saying? It's not, the $500 billion is like this fake made up number, but really what it is this Masayoshi-san, this guy. So this guy just, he is like this Japanese investor who basically just invests all the Japanese money, right? So like this guy, he's kind of a clown, to be honest, because he's basically like the last guy. You know how like the way that these startups work is that the VCs who are early basically inflate the valuation, and then the very last VC, right, the VCs that are like Series D, Series E, the guys putting in money at the very end, they're basically the suckers, right? Because they're putting in money at a valuation which doesn't make any sense. And like if the guys at the end, the late stage investors, are the suckers, this guy is like the king of the suckers, right? Like he invested in like Uber and like a bunch of shit. Like he basically waits until the very end when the only way that you can invest money is in like the billions of dollars. And then he just throws all this Japanese money in there. I don't know how this guy is still allowed to invest, because like, you know, like what the hell are you doing? You're just like dumping giant loads of money at the very end when you're basically done. But yeah, so what is Project Stargate? Project Stargate is basically Sam Altman, who is, you know, you got to give him his credit. This guy is probably the best venture capitalist ever, right? And what I mean by that is like, this guy can convince anyone, right? Like you put this guy in a room with like 10 criminals, and like he's going to figure out a way to be their king, right? Like this guy is like the smooth talking god, right? So imagine you put Sam Altman in a room with this guy, it's over, right? Like, you know, Sam Altman is going to riz him so hard that this guy's going to dump all his money on it. So what is Project Stargate? Project Stargate is Sam Altman rizzing the shit out of this guy to get him to dump a bunch of money into effectively building out a warehouse in Texas where they're going to try to do an Elon, right? They're going to try to make Elon H100 super cluster. Yeah, he's basically going to try to do this. But the problem is that Sam Altman isn't Elon, right? Like Elon is very good at operation, right? Like he's very good at like running factories. He literally has been doing that his whole life, like SpaceX, Tesla. Like the man is really good at like hiring people and like getting in those rooms and getting people to actually build things. Like there was an interview with the NVIDIA CEO Jensen Huang where he said that Elon was able to run this cluster faster than any other human, right? Where like other people take like multiple years to create these clusters. And he's like, I've never seen anything like it. Elon got this cluster running in like 1 year or something like that, like 18 months, like absolutely insane. So Sam Altman, yeah, like he's very good at convincing people. He's very charismatic. He's capable of getting the money, right? So he's capable of getting that 500 billion, which is not really 500 billion. It's like, you know what I'm saying? These guys are usually, they're investing on leverage. So it's like they basically take out a loan and then they invest the loan and then like they're doing all kinds of financial bullshit to like take $10 billion and make it seem like it's $500 billion. But is this guy, does Sam Altman have the operational skill to actually build out a factory with 10 million bajillion GPUs in it the same as Elon? I just don't think so. You know, so yeah. Yeah, Sam A, like this, he's next level smooth talker. And, you know, maybe this will get a little bit controversial here, but like part of it is I think that he's a gay man in San Francisco, right? I lived in San Francisco for some time. And San Francisco is kind of a very popular city for gay men. And a lot of them go there, and there's a huge community of gay men there, right? And if you think that kind of like the dynamics between men and women and, you know, like the ability to smooth talk and like the concept of riz, I don't know if you guys have ever heard this, I've used this now, but like charm or attractiveness, the ability to attract romantic or sexual partners, like if you think that the riz dynamics between men and women is kind of advanced, like the riz dynamics between men in the gay community is like at another level. You know what I'm saying? So like imagine this guy, right? Like this guy has basically spent his whole life just raising money and like rizzing people. And not only that, but like he's part of this whole San Francisco gay community where they're like the level of riz there is like, you know, they're playing these mind games and like smooth talking mind games that like, you know, like we can't even comprehend. So like that's why this guy is so fucking good at smooth talking. If Stargate is likely to get to AGI, I don't think Stargate. First of all, I think we already have AGI. I think ChatGPT was AGI. I think that was the AGI moment. But what do I think Stargate is going to be used for? I think the majority of Stargate is going to be inference compute. It's basically going to be like, by the time they finally build it, it's going to be like 2026, 2027. And at that point, there's going to be AI in so many different things, right? Like there's going to be AI in your Gmail. There's going to be AI on your phone. There's going to be AI in your car, right? So all that inference needs to happen somewhere. So Stargate, to me, is going to be less about kind of the pre-training compute that we've seen over the past couple years where people basically just need these giant GPU clusters to feed the entire internet of training data into the actual to train a next level frontier model. I think it's going to be more about just serving and inference, right? So like you have millions of customers who all want GPT-o1, o3 Pro, right? Where are all those reasoning traces? Where's all that compute actually happening in this cluster. So that would be my guess, is that like by the time this cluster gets complete, a lot of it is going to basically be inference compute for serving customers rather than necessarily kind of a bunch of pre-training compute. Even though that's still going to exist, I think DeepSeek showed us that you don't actually need giant clusters to do that, right? DeepSeek was able to create like something that's almost as good as GPT-01 Pro with just like a handful of GPUs, right? So I think that once you go into this RL paradigm, this new RL paradigm where you're just basically exploring the tree of knowledge and then using the chain of thoughts to distill back or to use reinforcement learning to then train the model. I think that paradigm requires less compute than the pre-training paradigm of just a couple years ago when you were basically feeding the entire internet worth of training data into a language model. I think this reinforcement learning paradigm is less compute heavy. So Stargate will be more about just kind of inference compute to serve customers rather than necessarily just a giant pre-training cluster where they're just training the next level model. Okay. I appreciate the questions, guys. You know, we were talking about all kinds of interesting, weird stuff. You know, those are the type of questions that I like. All right. I'll probably end it there, but I appreciate you guys. Thanks for watching. Join us next week for TBD. Thanks 770, Ed, Sarah, Elias, NLP, Julien, Nuclear, Ashvin, Oxoc, Aries, Sagar, Sarah, Yosef, Heuristics, Daniel, Majetti, NLP, Pratik. Who else? Heuristics, Sarah, NLP, Sam, Mark, Jan. Thanks everybody for listening. Hope you have a great day. Don't forget to like and subscribe and join Discord. Yeah, I don't know. I feel kind of cringe whenever I say that, so that's why I never say subscribe. Is there any fixed schedule for your live streams? Yeah, I usually stream on Fridays now. There's so you can go here into GitHub. I have it on my GitHub, this one here, docs. So this is the basically all the streams. So you can, for example, go into, for example, agent framework. So that was the stream that I did there. You have the thumbnail, you have all the different links. But here's my schedule. Stream on Friday mornings. It's different depending on where you live, of course. And then these are different places where I source my papers. All right, guys, I appreciate it. Thanks for watching and see you later.